Hi, I'm going to talk about capacitors in general and then give you a specific example of using the formulas associated with capacitors. So capacitors in their simplest possible design are just a pair of parallel plates. And typically you charge one side positive and one side negative, usually by a battery or something like that. So here's our stereotypical, very simple capacitor. And so the electric field from each of these will be equal to the charge divided by twice the area times the permittivity of free space. Okay, and that's something that you can get from the chapter on electric fields. And if you take the vector sum, then the electric field inside will be twice that. So it'll be the charge of an individual plate, so don't worry about positive or negative here, just the magnitude of the charge on either of the individual plates. The capacitor in total is uncharged, divided by the area of an individual plate times the permittivity of free space. That's 8.854 times 10 to the minus 12 coulomb squared per Newton meter squared. Okay, so that's the electric field inside. That's the vector approach to thinking about capacitors. Electric field above and below will be zero. Okay, what I'm going to be focusing on is the scalar approach to these. And so one thing we can do is determine the potential difference in terms of the electric field. And since the electric field is constant between these plates, you can use this mathematical relationship, potential difference divided by distance, and then derive that the potential difference is the electric field times the distance of separation. So this distance here would be d. Okay, another thing that you can determine is a physical property called capacitance, and it is by definition the charge of an individual plate divided by the potential difference. And so you can take these three formulas here and combine them. I'm not going to go over the full derivation, but in general, any capacitor, its capacitance is charge over potential difference. For a parallel plate capacitor, based on the formulas I've already given you, you can use the permittivity times the area of an individual plate divided by the distance between the plates. So this is definition, always true. This is based on the physical construction of a parallel plate capacitor. Okay, one more set of formulas, and that is that capacitors function as short-term electrical energy storage devices. Typically, there's not a lot of energy. It's pretty hard to store like a macroscopic amount of energy in a typical capacitor, like a kilowatt hour or something like that. So usually fairly small amounts, even by joules standard, which are also a very small unit. So the potential energy stored is 1/2 the charge of an individual plate times the potential difference between the plates. And this looks a little weird because this factor of 1/2 just kind of popped up out of nowhere. And I'm not going to do the complete derivation, but really think of the half as associated with delta V. So it's the average potential difference of these plates that it had as you were charging the plate. So assuming they started electrically neutral, you charged it. The first charge to shove onto those plates was very easy because the potential difference was small, and then it built up to a maximum potential difference, which is what you have in the end. So average potential difference times the final charge is the potential energy. Okay, you can combine this with the formula for capacitance to get a couple other formulas, such as 1/2 C delta V squared, or Q squared over 2C. So depending on the information you have, the energy stored in a capacitor can be solved many different ways. Okay, so that's kind of the general idea with capacitors. If it's parallel plate, it has an electric field. You can calculate the potential difference based on that electric field. There's a definition of capacitance, a formula for capacitance in terms of physical construction, and 3 different ways to calculate the potential energy stored in a capacitor. Okay, so now let's look at a specific example. So I'm going to just start with a physical design for a capacitor. So let's say that we're given a capacitor with a capacitance of with physical dimensions, 10 centimeters by 10 centimeters, and then we'll have a distance apart of 1 millimeter. Okay, so 10 centimeters here, 10 centimeters here, and 1 millimeter apart. And we're going to connect it to a battery. And so battery, and we typically use this symbol, capital epsilon, for the battery potential difference. We'll just use a 9-volt battery. Okay, and I'm going to connect this capacitor to this battery, and we're going to calculate a whole bunch of different stuff. Okay, so first I'm going to calculate the capacitance. So I have I was given the physical dimensions of the capacitor, so I can calculate the capacitance. So epsilon naught A over D, and in SI units, 8.854 times 10 to the minus 12. Area is 0.1 squared in SI units of meters, and distance would be 0.001 meters or 1 millimeter. And I get that the capacitance is equal, you might be able to do this in your head, is 8.854 times 10 to the minus 11 farads. So farads are the SI unit, so it's really 88 picofarads, which is a pretty tiny capacitor. Okay, so parallel plate with vacuum inside is generally not the most effective way to build a capacitor, but it's the simplest to analyze, so that's why we're doing it. Okay, let's calculate a few other things. Potential difference, if we connect the capacitor at both ends to the battery, well, then it just has the battery potential difference. So that's pretty easy. We can assert that the battery creates 9 volts of potential difference across this capacitor. And then we can calculate the electric field using this formula. So electric field will be the potential difference divided by the distance between. So 9 over 0.001. Okay, again, pretty easy to do perhaps in your head. 9,000. And the units would be volts per meter, or typically from the vector chapter, forces and fields, would be newtons per coulomb. Those are equivalent. Either is fine. Okay, we can calculate the charge. And I would use the definition of capacitance, solve for charge. So charge would be capacitance times potential difference. So 8.854 times 10 to the minus 11 times 9. And I get that the charge is equal to 8 times 10 to the minus 10 coulombs. So a little bit less than a nanocoulomb of charge. So not a lot of charge. Low capacitance, not a lot of charge. And then we can calculate the energy using, take our pick. We've got capacitance, potential difference, and charge. I'll just use the first one. And throw that into your calculator, and you get, and I'm running out of space here, you get that there's an energy of 3.6 times 10 to the minus 9 joules. So 3.6 nanojoules of energy stored in this hypothetical capacitor. Okay, so that's it. Hopefully you got a handle on a lot of these different formulas associated with capacitors in general. This one is associated with only parallel plate capacitors. Same with this one, so be careful. Some of these formulas aren't universally true. And then hopefully this example was illustrative of how to use physical dimensions to calculate capacitance, and then use that to calculate a whole bunch of different physical quantities associated with this. Okay, that's it. So have a good day. I'll see you next time.